3.1, higher order derivatives, velocity and acceleration. So derivatives are used in the study of motion. We've already seen velocity, which is the rate of change of displacement at a specific point in time. Okay, so velocity is like the first derivative of displacement. Okay, so we looked at rates of change as an object moves in a straight line, either vertically, such as a rocket going into space, or a car on a straight section of road. So, higher order derivatives. The second derivative of y equals f at x is the derivative, and check out this notation, y double prime. Okay, this means first derivative, second derivative, equals, and then what we're going to do is we're going to take f at x, but it's f double prime at x. So we're going to take two derivatives of it. And the notation for the second derivative using Leibniz notation is, it's like d squared y over dx squared, okay, which comes from, if you think about d by dx, this means take the derivative of dy by dx. Okay? So, example 1, determine the second derivative of f at x equals x over 1 plus x when x equals 1. Okay, so I'm going to actually bracket the denominator, and I'm going to rewrite this function as, actually I'll write it over here, as f at x equals x bracket 1 plus x to the negative 1. Okay, so I haven't done anything yet. All I did was rewrite this as product rule. Okay, if you remember product rule, u prime v plus uv prime, okay, and that is the derivative of uv. Okay, so the x is going to be our u, the 1 plus x to the negative 1 is going to be our v, and then we can go ahead and find f prime at x. So I'm going to do this all in one shot. So we have derivative of u, so derivative of x is just 1, and then times v, so times this as it is, 1 plus x to the negative 1, plus u as it is, so that's x, times the derivative of v. Okay, so this is the chain rule. So we move the negative 1 to the front. We write the bracket as it is, 1 plus x. We subtract 1 off the exponent, so that's to the negative 2. And then if you think about doing the derivative of the inside here, 1 plus x, the derivative would just be 1, right? It would just be the coefficient of x. So I'm just going to clean this up just a bit, but not fully simplify, okay? So 1 times anything is just this number, 1 plus x to the negative 1. And then I'm just going to collect the x times negative 1 times 1, which is minus x bracket 1 plus x squared to the negative 2. Okay? Okay, now in this step, I'm going to factor out, we don't have to, but it's going to be nicer at the end. Okay, so what is common in these two terms is 1 plus x, and then we have to take the smaller of the two exponents. So we have negative 1 and we have negative 2. So negative 2 is a smaller number. Okay, so the common factor is 1 plus x to the negative 2. And then what's left over is, in the first term, 1 plus x. And in the second term, minus x. Okay, I'm going to bring this into the denominator. So I have 1 plus x to the negative 2. Actually, no, because I'm not going to use quotient rule. I'm just going to leave it in the numerator. 1 plus x to the negative 2. And then we have x minus x, which goes away. We just have 1. So if we multiply by 1, I'm just going to leave it like this. 1 plus x to the negative 2. This is our derivative of this original. So at this point, what we have is we have a new function. We have f prime at x, okay? So if we want to find the second derivative, what we're going to do, and I'm going to do it on this side of the page, okay, we're going to take f prime at x, which is, and I'm just going to rewrite 1 plus x to the negative 2, and we're going to take the derivative of that, and that will yield f double prime at x, so f prime prime. So all I'm going to do is bring down the negative 2, write the bracket as it is, 1 plus x, subtract 1 from the exponent. This is technically chain rule, but the derivative of the middle is just 1. And then that's it. Let's just go ahead and simplify this. So negative 2 bracket 1 plus x to the negative 3. So now it says determine the second derivative when x equals 1. So all I'm going to do is take f double prime and sub in 1. So I get negative 2 bracket 1 plus 1 to the negative 3. So negative 2, 2 to the negative 3. Okay, if you think about this, we can bring this into the denominator and raise it to the positive exponent. So I get negative 2 over 248, which is negative 1/4. Now let's talk about velocity and acceleration. So motion on a straight line. When studying motion along a line, we assume that the object is moving straight, such as a number line, okay, where there is an origin of reference as well as a positive and negative directions. Okay, so usually what we would see is some like 0, right? So the displacement would start at 0, that being like, that's the starting position. Okay, and then we're going to move to the right, which is going to be like positive direction, and then to the left, which is negative direction, maybe another positive, okay, and back and forth. So the position of an object on the line relative to the origin is a function of time and can be denoted as s at t. So whenever you see this s at t, this is displacement. Okay, so position. S at t is the distance from an object with respect to time. So it's like from an object, that could be like leaving home, leaving school, the mall, whatever it is. Like it doesn't have to be specifically an object, but it could be a place. But we just generalize it with object. And it could be like a gas station, right? Like if you're driving, how far from the gas station, right? And then the gas station or that point of reference would start at 0, which is like the origin. Okay, now velocity. So check out this notation. The velocity at time t, this does not look like a derivative. That's because we changed the variables. We're now saying like we're going to use v, so you can interpret it as velocity. But what velocity actually is the first derivative of displacement, which is ds by dt. Okay, and that just means that it's the rate of change of s at t, like the displacement, with respect to time. Okay, and just remember, velocity can be positive or negative, but the absolute value of velocity is speed. Speed's always positive. Okay, and then finally, acceleration. So acceleration, a at t, again, it does not look as though there's a derivative on acceleration. That's because we changed the variables. We're telling you now the letter that we're using is a, so that means acceleration. But what acceleration actually is the derivative of v, right? The derivative of the velocity, which is dv by dt. But in order to get the velocity, we would have had to derive the displacement. So acceleration is actually the second derivative of displacement, which is d2s over, well, d squared s over dt squared. Okay, and what this is the rate of change of the velocity with respect to time, right? how that velocity is working. Now let's talk about direction, okay? When an object is moving to the right, so what happens is the velocity is positive, okay? So you can put like a positive sign. This is what this means. Velocity is greater than 0. But when it's moving to the left, the velocity is negative. Because remember, velocity has both a direction. Here, velocity has a direction and it has a magnitude. Okay, so remember, magnitude is the number, direction is going to be the plus or minus. Is it going to the right or going to the left? And we naturally assume, like, we naturally talk about going to the right as positive, because if you remember a number line from like elementary school, we're going positive numbers. If you think about a Cartesian plane, which is like an x and y axis, going to the right is positive numbers. Okay, going to the left of the origin is always negative numbers. So we do the same with the velocity. Okay, and when an object is stationary, we've seen this before, the derivative equals 0 or the velocity equals 0. Right? That it's either stationary or it's like a turning point. So, just throwing this out there, remember the turning points in like a polynomial here and here would have the tangent line would be horizontal because the slope would be 0, right? Just momentarily, the direction changes from positive to negative. Okay, now let's talk about the object accelerating. So the object is accelerating when the acceleration and the velocity are both positive or both negative. Because if you think about it, both positive, what we're going to be doing is we're just going to be accelerating, like it's accelerating to the right. Oh, we'll go accel to the right. I'm just going to put R. Right? Or if they're both negative, what that means is that we're just picking up speed going to the left. So what both negative would just be acceleration to the left. Okay? And overall, what we want to do is we want to make sure that like we're accelerating as long as the product obviously being multiplication, of the acceleration and the velocity is positive. Right? So obviously positive is going to yield a positive, and negative will yield a positive. Okay, now deceleration. Okay, the object is decelerating when the acceleration is positive and the velocity is negative, or vice versa. So what we're going to have to see here is a positive negative or a negative positive, because the product of acceleration and velocity have to be negative in order for it to be decelerating. Okay, so example 2. An object is moving along a straight line. Its position, S at t, to the right of a fixed point is given by the graph shown. Okay, so obviously the fixed point starts at 0. This question asks, when is the object moving to the right? When is it moving to the left? And when is it at rest? So I'm going to set this question up to the right, to the left, and at rest. And I'm going to write out the intervals. So moving to the right is going to be when it moves away from this reference. So from here to here, it's moving to the right. So 0 to 2. But here's the thing. We're not going to include 0, and we're not going to include 2. At 0, it's a starting point, so you haven't really moved yet. And right at 2, it's actually a turnaround point, where we're going from moving to the right to moving to the left. So I'm going to add that to the rest. Right? At 2. the horizontal line there. Okay, now let's keep going on the graph. So from 2, but not including 2 because it's at rest at 2, from 2 all the way till this point here. Okay, and again, just like in functions, if you remember, we read what's going on in the graph, but we quote, like usually in regards to the y value, in this case the t value, but we quote in the x's. We talk about what's going on in certain domains. So from 2 to 6, not including 6, because again at 6, we have a horizontal tangent line. So from 2 to 6, we're moving to the left, right? That negative direction. This is a negative direction. Okay, and then we're at rest at 6. And then from 6 to infinity, because there's an arrow here. So 6 to infinity, we would be moving in a positive direction, or to the right. Right? So this is how displacement is depicted on a graph. Example 3, the position of an object on a line is given by s at t equals, then we have a polynomial, 6t squared minus t cubed. Okay, and this is saying that the position is going to be when time is greater than or equal to 0. Okay, so this is very, very common. You can't go back in time. Okay, S, so the displacement is in meters and the T is in seconds. Another common combination of variables, or like units and variables. So A, determine the velocity and acceleration of the object at t equals 2. So we know that so I'm going to just rewrite S at t equals 6t squared minus t cubed. So for A, we need to find the velocity at time t. We know that that's the first derivative of displacement. So let's go ahead and find the first derivative. Bring the 2 down. 2 times 6 is 12. T, and then we'd subtract 1, so it's just 12t. And then bring the 3 down, so it's minus 3t, and then subtract the 1 off of the 3, and we get squared. And if we want to find the velocity at t equals 2, we can simply find velocity at 2, which also is the derivative of the displacement at 2, and we can just sub in the 2. Okay, so 12 times 2 is 24, minus 3 times 2 squared is 4, minus 12. I get 12, and because it's velocity, we need meters per second. Now let's find the acceleration at t equals 2. Okay, so the acceleration, let's change the colors. Okay, the acceleration is actually the first derivative of velocity, which is the second derivative of displacement. So let's locate the velocity, which is right here, and let's take the first derivative of velocity. So what's the derivative of 12t? Well, it's just 12. And what's the derivative of negative 3t squared? Well, bring the 2 down. Negative 3 times 2 is negative 6. And we're left with t, right? Because if we subtract 1 off the exponent's 1. And at this point, we can find the acceleration at time t, which is actually the same thing as saying the derivative of the velocity at time 2, okay? And the second derivative of displacement at time 2. Okay, so 12 minus 12, which is 0 meters per second squared. Okay, now, at what time, oh, this is supposed to be t, is the object at rest? So, at rest, when we're talking about rest, we're talking like the velocity. Let's just put v at t equals 0. So, for B, we're going to take v at t, which is, and I'm not going to write these again, okay? I already wrote like v at t equals s prime just to really ingrained in your minds that is the first derivative versus the second derivative, but you don't have to write that ever in a test. You can write one or the other. So 12t minus 3t squared. So when we're looking for when this is at rest, what we want to do is we know that the velocity is going to equal 0 when we're at rest. Oops, I forgot the t in here. So if we think about factoring this, I'm thinking about factoring out, you know what, let me first put this in order. I like this in, it's called standard form. I like it when it's like t squared and then t when we're dealing with a polynomial. So I'm going to go ahead and factor out a negative 3t. Okay, so I get negative 3t bracket, and I'm left with t minus 4. So there are going to be 2 times in which the velocity equals 0. T equals 0, which is the starting point, and t equals 4. So we can say, therefore, at t equals 0 and 4, the velocity, instead of the velocity 0, you know what? Let's actually interpret it. Okay, the object is at rest. And that's better because then we like apply it directly to the question. Okay, now, in which direction is the object moving at t equals 5? So in which direction? So which one of these equations gives us the direction that something's moving? So we know from that box above that we just read that the velocity, when velocity is positive, we're going the right direction, like we're moving to the right, and when velocity is negative, we're moving to the left. So we can go ahead and sub in 5 to the velocity, which, again, 12 times 5 minus 5 squared, that's 25. So 12 times 5 is 60, minus 3 times 25 is 75. I get negative 15 meters per second. Okay, and so therefore, at time equals 5, the object is moving to the left, okay? Because this is a negative number. Negative velocity moving to the left. Positive velocity moving to the right. Okay, so D, when is the object moving in a positive direction? Okay, so when we're talking about positive and negative directions, okay, what's going to happen is we're going to actually take a look at, okay, so we know we start at 0 and we can't go negative. And we know there's a turnaround point at 0, and we know there's a turnaround point at 4. So you know what? Let me do this, okay? So what we have to test is we usually have to test between all of these, okay? It's very similar to doing like inequalities in advanced functions, where we're going to have to test a velocity over here. Is it positive or negative? Velocity here, is it positive or negative? And a velocity here, is it positive or negative? Because we know that there's only 2 turnaround points, going from positive to negative or from negative to positive. And when I say positive to negative, I'm really talking going to the left or to the right, okay? We don't actually have to test the velocity over here because we know that time is going to be greater than or equal to 0. I had to check the domain, okay? So the function is not going to be defined over here. So let's go ahead and test one of the velocities between 0 and 4. So let's test the velocity at 1, okay? So we know velocity is 12t, okay? So 12 times 1 minus 3t squared. Okay. 1 squared. So I get 12 minus 3, and I get 9 meters per second. So it is moving to the right between 0 and 4. And we already tested a point over here. We tested the velocity at time 5. So we got velocity at time 5, we got that negative 15 meters per second, right, in the previous question. So we can say that we're going to the left on 4 to infinity. So the actual answer to our question is this one right here. It says, our question asks, when is the object moving in a positive direction? Okay, the object moves in a positive direction on 0 to 4. Okay, and when does the object return to its initial position? So we haven't even determined what the initial position is. So the initial position is when the displacement is going to be at time 0. So let's go ahead and sub that in. We have 6/0 squared minus 0 cubed, that's 0. So our initial position is 0, 0. It's actually the origin. All right, so what we would want to do is we want to know if there's another point at which the displacement is 0. So what we're going to do is we're going to say, okay, so we have the displacement, and we're going to solve it for when the displacement is 0. So let's just write out 6t squared minus t cubed. Okay, and we want to equal this to 0. So if you think about it, we can factor out t squared in each of these. Okay, and we get 0 equals t squared bracket 6 minus t. What that's going to give us is t equals 0, which we already have. And then also, if you have to solve for this, 6 minus t equals 0, so t equals 6. So the object is going to return. In other words, the object is also going to have a displacement of 0 at t equals 6. Object will have displacement of 0 at t equals 6. In other words, it's going to return to its initial position. Example 4, discuss the motion of an object moving on a horizontal line if its position is given by this equation here. Okay, as a t equals, I want to rewrite this, t squared minus 10t, and it's on the domain 0 to 12. Okay, where s is in meters and t is in seconds. Right? And then a couple things that we're going to include is initial velocity, final velocity, and any acceleration. Okay, so what I would do first is I would find the first derivative of this, and I get 2t minus 10. And then I would also find the second derivative of the displacement, which is acceleration, and I get 2. So let's start with talking about everything we know about velocity, okay? So the velocity, or s prime at t. So we can talk about the initial velocity first. So s prime at 0 is 2 times 0 minus 10. So the initial velocity is negative 10. So initial velocity is negative 10 meters per second, or it's 10 meters per second in the left direction. Okay, let's then talk about the final velocity. So the domain ends at 12. So let's sub in s prime at 12. So 2 times 12 this time minus 10, which is 24 minus 10, which is 14. So final velocity is 14 meters per second in the right direction. Okay. Another thing that we can do for the velocity is we can determine when the velocity equals 0. So 0 equals 2t minus 10. Okay, bring over the 10, we get 10 equals 2t, and then divide out the 2's. So what we get here is that there is going to be a change in direction. So change in direction at t equals 5. Okay, so if we think about our interval from 0 to 12, and then there's going to be a change in direction at 5, what we can do is we can test a velocity here. So maybe velocity at 1, and then test a velocity here, velocity at, I don't know, let's go 6. Okay, and we can see which direction we're moving in on these intervals. So the velocity at time 1 is going to be 2 times 1 minus 10, which is negative 8. So this is negative, right? We don't really even care that it's negative 8 specifically. We just care that it's negative. And the velocity at time 6 is 2 times 6 minus 10. So that's going to give us 2. So this is a positive interval. And we kind of already saw this when we subbed in the 0 and the 12, but I always like to do one of the points between these, just in case at 0 or 12 we might get like a turnaround point as well. So what we can say about this is we're moving, the object is moving, and it's a threefold here. To the right on 5 to 12, to the left on 0 to 5, and is at rest at t equals 5. Okay, this is everything to do with velocity. Now we're going to change color and we're going to move on to acceleration. So acceleration at time t, which is s double prime at t, is a constant 2. What does this mean? This means that since the acceleration is a constant, the object does not accelerate on 0 to 12. And what this also means is that the velocity is increasing or decreasing at a constant rate. Right? And obviously we can see that because when we take a look at the velocity, this is a line, right? Equation of a line. This is a linear. Okay. One last thing that we could do. Oh, I want to point out these should be square brackets because we're going to include 0, we're going to include 12. Oh, but not 5 because at 5 it's the object's at rest. So if we actually took the displacement and we subbed in 0 and we subbed in 5 and we subbed in 12, we could have a better understanding of how this object is actually moving. So if we subbed in 0, we get 0. If we subbed in 5, we get negative 25. And if we subbed in 12, we get 24. So when we're actually talking about where this object is, let's call this 24. Okay, this object starts at 0, it goes to 25, and then it goes to 24. It takes 5 seconds to get to 25. And at 5 seconds, it's at negative 25. And this is not even a full second. This is just a split second. And then from 5 seconds, so from 5 seconds to 12 seconds. This object's moving to the right. So let's call this, instead of quoting this as it takes 5 seconds, let's quote this as it goes from 0 seconds to 5 seconds. So that's how the object's actually moving. So we can call that the actual path of the object. Example 5, a baseball is hit vertically upward. The position S at T in meters of the ball above the ground is this function. So I always write this function down here so that I can work with it. Okay, so this is the function negative 5t squared plus 30t plus 1, where t is in seconds. Okay, and then we know S is in meters. So A, determine the max height reached by the ball. Okay, so this is a parabola. We know that we're dealing with a parabola that starts at the height of 1. Okay, the negative 5 is an approximation for the gravity, right? We're usually dealing with negative 4.9 t squared, and we know that the derivative of that is going to be negative 9.8 t, right? And if you think about gravity, negative 9.8 meters per second squared, gravity is going in the negative direction because it's going to go back down. Okay, so we know that we're trying to look for this turnaround point here. So we are trying to look where we have a horizontal tangent. Okay, so let's go ahead and solve for the derivative of the displacement, which is actually our velocity, because we know right here momentarily, just for a split second, our ball is going to stop, change directions, and then go back down, pick up speed again. Okay, so we're actually finding the velocity. So let's go ahead and bring this 2 down, negative 5. So we have negative 10t, and then the derivative of 30t is just 30. Derivative of 1 goes away. A lot of times I won't even comment on this. I just leave it out. Okay, so if we know that the velocity at time t is negative 10t plus 30, let's find when that velocity equals 0. Okay, so bring over the 10t, divide both sides by 10, and we get t equals 3. So right here at time equals 3, we're going to have that horizontal tangent. Okay, we're going to have that turnaround point. So A asks, determine the maximum height reached by the ball. Well, all we're going to do is we're going to take t at 3 and be like, okay, well, what's the height? What's the displacement? And we're going to sub this back into the original. So negative 5, 3 squared plus 30, 3 plus 1. Okay. And I get 46 meters. So therefore, the max height is 46 meters. Okay, now determine the velocity of the ball when it is caught 1 meter above the ground. Okay, so we know from this, this is ax squared plus bx plus c form of a quadratic. So we know that it's launched from 1, so it's going to be caught at 1. So maybe a man is standing here with his glove, and he's catching it 1 meter above the ground. So we have to find when does this occur, and then we have to find the velocity of it. So we know that the displacement, the height above the ground, is going to be 1. So 1 equals negative 5t squared plus 30t plus 1. Okay, bring that over. 0 equals negative 5t squared plus 30t. And you know what? You don't even really have to bring this over. If you think about there being a positive 1 on this side of the equation, positive 1 being on that side of the equation, those two are balanced, so they can cancel out. If you do bring it over, it is subtract 1. Okay? At this point, t, we have to solve for t. So let's factor out a negative 5t out of both of these terms. And we get negative 5t, t minus 6. So our zeros are going to be t equals 0 and t equals 6. Those are not the zeros of the actual function itself, like here and here. That's not what that means. Since we subbed in 1, what we essentially did is we took this x-axis and we moved it basically right here. We moved it up 1, and we're saying, okay, where are the zeros here? So 0, because we're launching the ball from a height of 1, and then we're catching it at 6 seconds. Right? And then launching, I mean like 0 seconds. So this catch occurs at 6 seconds. So what we have to do is we actually have to find the velocity at 6 seconds. Okay, so this is the velocity formula back up here. Negative 10t plus 30, negative 10.6 plus 30. Okay, so that's negative 60 plus 30, which is negative 30. So we can say the velocity of the ball is traveling at 30 meters per second downward. Okay, this downward takes over that negative. So it's in like straight substitution.